So this video is on calculating heat lost or heat gain during a process. It also allows you to calculate some of the other variables in a series of equations. Now, unlike what you do in math, in science, as a general rule, you're going to be given 3 out of the 4 things in the equation and have to algebraically solve for the one you don't know. That one thing that you do not know is going to be basically your x. There's going to be no y. So there are 3 formulas here. Q equals mc delta T. Now this formula has the delta T in there, which means it's for when things change in temperature. MHF and MHV are for when things don't change in temperature. Those are for these 2 formulas deal with phase changes. Right? So when you're dealing with this graph that we just did the other day, right? This segment right here is where you're going to use MHF, because that's going to deal with the HF stands for heat of fusion, or the amount of energy or joules required to melt a gram of a substance, which, by the way, will be the same amount of energy needed to freeze a gram of a substance. The only difference being that in one case the energy goes in, in the other case the energy goes out. MHV will be used on this segment here because that is the amount of energy required to boil 1 gram of a substance. And it will be the same thing as the amount of energy that's released when you reverse the process and condense it. The MC delta T formula can be used on any of the diagonal segments. So what I'm going to do is show you 4 problems in which we determine which formula to use, and we're going to use the numbers that we determined from the previous video, in which we determined the heat of fusion of our substance to be 30.0 joules per gram, our heat of vaporization to be 40.0 joules per gram, and the specific heat capacity to be 0.833 joules per gram per degree Celsius, meaning it would take this much energy in joules to raise the temperature of 1 gram by 1 degree Celsius. This would be the amount of energy required to melt a gram, and this would be the energy required to vaporize or boil a gram of a substance. So let's look at a question and figure out which formula we're going to use. So it says how much energy will be required to melt. Now as soon as I see melt, I'm thinking this is about fusion. And I've got 5 grams. How much energy will be required to melt 5 grams of a substance at its melting point? Well, since I'm melting, I'm going to use this formula I'm circling right now, Q equals MHF, where Q represents the heat in joules. HF represents the heat of fusion, which we have right over here, and M represents the mass. And it's really just a factor label problem, right? So if we want to know the amount of energy, we're basically trying to figure out what Q is. And all we have to do is multiply M times HF, and that will give us the thing that we're being asked for. Now, since the mass is 5 grams, we basically substitute in our value. So we have 5.0 grams, and we're going to multiply that times the heat of fusion. Now notice how much this looks like a factor label problem, because it really is, right? We're basically saying it's going to take 30 joules to melt 1 gram. So how much will it take to melt 5 grams? Well, the grams cancel out, and we get our answer in joules. And I can do 5 times 30 in my head. I think most of you can too, right? Right, that's 150 joules. And if I'm following the whole sig fig thing, since this only has 2 sig figs, right, and all these other numbers up here have 3, I'm going to round this to 2 sig figs, so it would be 1.5 times 10 to the second joules if we're sticking to significant digits. All right, let's try a different problem. This one says how much energy will be required to boil. Okay, since I'm boiling now, right, instead of using the same formula I said before, I'm going to erase all this stuff now. Okay? So which formula am I going to use? Well, I'm going to use the formula that deals with boiling. I'm going to use this HV, which is my heat of vaporization. And I'm going to use this formula right here because that is for the phase change of boiling or vaporization. And I do the exact same thing. I go, okay, I'm going to use Q because I want the energy. Right? And I get my answer in joules, which is the unit of energy. And that's equal to the mass times the heat of vaporization. Now, it says the sample. So I'm not giving you the mass here, but if it's the same sample, it's the same mass. That doesn't change, right? If you have 5 grams of a liquid, when it boils, you have 5 grams of a gas, right? You don't lose particles. Matter doesn't magically disappear, right? So take your 5.0 grams this time and multiply it by the heat of vaporization. So I'm putting the 5 here and the 40 joules per gram here, and I'm kind of being lazy about sig figs. This would be 40.0, and in this case I can do 5 times 4, and again I didn't even break out a calculator because 5 times 4 is 20, so 5 times 40 is 200. So I've got 200 joules because my grams cancel out, and sig figs, that'd be 2.0 times 10 to the second joules. Alright, so that's how we deal with those types of questions where we're dealing with melting or boiling. And by the way, if this was 5 grams to freeze, it would be the exact same amount of energy. The difference is, instead of absorbing the energy, it would release. And for the boiling, it would still be 200 joules, but if you were going to condense, those 200 joules would be released. Alright, let's go to some formulas. Let's deal with some questions that involve this formula up here, the Q equals MC delta T. Alright, so we're going to use Q equals MC delta T on this page. Okay, and let's remember what everything means. The M is the mass. The C is what we call the specific heat capacity. And that is the amount of heat required to raise the temperature of 1 gram by 1 degree Celsius. So the unit's going to be joules per gram per degree Celsius. And that's a specific heat of that substance as a liquid. And by the way, specific heat as a solid and a gas, not the same value. Specific heats also vary by substance and even the phase the substance is in. Delta T is the change in temperature. Okay, so in our first question is how much energy would be required to raise the temperature, which means right there, that implies delta T. We have this number here, 15 grams. That's our mass. And we're raising the temperature from 60 degrees Celsius to 85 degrees Celsius. So our delta T in this particular case is going to be equal to what the change is. And make sure we're clear, since we're raising the temperature, you should recognize that we're adding heat. If we lower the temperature, then that heat would be being released. Okay, this is an endothermic process. So delta T here is going to be 25 degrees Celsius. That's a 5, by the way. And that's 85 minus 60, right? Gives you 25 degrees. And then we just plug the numbers into the equation. So we have Q equals M, but we already know our M. Our M is 15.0 grams times C. C in this case is 0.833. Now I'm going to make the parentheses, right? Okay, joules per gram per degree Celsius. And then you're going to multiply it by the change in temperature. You're going to multiply that times 25 degrees Celsius. Now notice, once again, the units that we don't care cancel each other out. So the grams will cancel with the grams. The degrees Celsius will cancel this out. And this one I'm going to use a calculator for because, right, so I'm going to go 15 times 20 times 25. And then I'm going to multiply that by 0.833 times 0.833 equals, and I get 312.375 joules. I'm going to round that to the proper sig figs, and I really did a bad job here. I'm going to put a dot here and make this at least 2 sig figs, okay? So we have 2 sig figs in our answer, which would be, so we would round this to 310 joules would be a good answer, okay? By the way, they could ask you for the answer in kilojoules, and you should be able to convert this. So if you had to convert to kilojoules, you'd be like, oh, wait, 1 kilojoule is 10 to the 3rd joules, and so your answer in kilojoules would be 310 times 10 to the minus 3 kilojoules. And of course, we could put that in scientific notation if we had to, but I'm not going to do that right now. Now, this next question, number 4, is a little bit more difficult, all right, and it requires a little more thought. Because it's asking for something different. Now, students who don't follow this closely will think to themselves that they have all the numbers to fit into the equation, and they won't understand what they're actually solving for. So here, let's look at this question. We have 140 joules of energy. It is being added to a 15-gram sample at 55 degrees Celsius. What will be the final temperature of the liquid? Well, since we have, basically, here's our formula right here. We essentially have our mass, right? We have our Q, right? We have our specific heat, because our specific heat is this number right there. We don't have delta T, though. what we have here is the initial temperature. I'm going to write TI here for the initial or the starting temperature. Now, since this is where you have to think, since you're adding heat, you can assume the temperature is going to go up. And by solving for delta T, you know how much it's going to go up by. So here we have, I'm going to plug the numbers into the spot. So 140 joules, that's our Q. So you have 140.0 joules equals M, 15.0 grams, times C, 0.833 joules per gram degrees Celsius times delta T. And you can think of delta T as being X. This is the thing we're solving for. So how do we do this? Well, we have to move things around. And the way you can do this is, it's kind of your decision, but in the end, you're going to end up dividing 140. When you move these things over, you're going to divide 140 by 15.0 grams, and you're also going to divide by 0.833 joules per gram per degree Celsius. And what's going to happen is the joules will cancel out, the grams will cancel out, and I'm basically just getting rid of all this other stuff by dividing both sides by that. And I kind of skipped that thing. I just sort of cross-multiplied in my head. Now, you can think of this as if you had 5 equals, 6, times 7 times x. Well, basically, that would be equal to 5 divided by 6 times 7 equals x. And that's what we're really doing here. So I'll break out my calculator again. I have 140 divided by 15 equals, and then divide by 0.833, and I get 11.2 degrees Celsius. That's got 3 sig figs on it, by the way. And here's the thing. This is how much the temperature is going to change. This is our delta T, right? So in the end, right, we now know what our delta T actually is, all right? We know that the temperature is going to go from 55 degrees Celsius, and we're going to add 11.2 degrees Celsius because that's how much it's going to change by. So our final answer is going to be 66.2 degrees Celsius. However, if we're being nitpicky about sig figs, since there's nothing here in the tenths place, we're going to round this and give our answer as 66 degrees Celsius, and that's our final answer. Alright, this was a little bit longer, but it involved math, so I want to go slow and make sure everything was clear. We'll do some problems tomorrow in class.